Hey guys, welcome back to General Chemistry 1. We are going to start a series of periodic trends. So we're going to talk about 3 trends across the periodic table: atomic radius, ionization energy, and metallic characteristics. This video is going to be about atomic radius. Before we can talk about the trends, I need to at least define what atomic radius is. So atomic radius is going to be the distance from the nucleus, so the center of the atom, to the outermost shell, to that valence shell. So the distance from the nucleus to that electron that is furthest away from the nucleus. That's going to be our atomic radius. So the bigger the radius, the further away those electrons are. The smaller the radius, the closer they are to the nucleus. All right, so here is one graphic that we can use. First, let me tell you what's going on here. So again, these are our main group elements. So here's group 1, group 2. We took out that transition element, so the D block element, and we shoved the two sides together. So this is like jump across the transition elements: 13, 14, 15, 16, 17, and 18. Here's our noble gases. So why did I do that? Well, remember, main group elements are the predictable ones. So those are the ones we're going to look at when we talk about these trends. So I noticed 2 trends going on here. I noticed there's a trend from top to bottom, and I noticed there's a trend from left to right. The one from top to bottom is a lot easier to talk about, or understand. So let's talk about that one first. So let's look at just group 1 then. So we've got hydrogen, lithium, sodium, all the way down to cesium. So as we go from top to bottom, the atomic radius gets bigger. Not surprising. But why? Well, if we think about the atomic radius, we're talking about the nucleus to the valence electrons. So in hydrogen, where are those valence electrons? Those valence electrons are in the first energy level. So we put one kind of shell around that hydrogen, and boom, the electrons are right there. As we move down the periodic table, if we get to like cesium's valence electrons are in the 6th energy level. So now we've stacked 1 on 2, on 3, on 4, on 5, on 6. So we have gotten further and further away from that nucleus, and now our valence electrons are way out here on the sides. So that's why we see that atomic radius go up as we go down. Energy level gets bigger. We're stacking sublevels on top of each other. The trend from left to right is not so easy to understand. It's not as intuitive. So let's look at here lithium to neon. And the trend that we see from left to right is it gets smaller. What's going on there? Well, to understand why it gets smaller, we've got to talk about one other thing. I consider this like a tool we have to put in our tool belt before we can understand atomic radius. So the thing that affects left to right is something called effective nuclear charge. So the effective nuclear charge is basically the interaction between valence electrons and the protons in the nucleus. So interaction of valence electrons and protons in the nucleus. So looking at, this is neon. So this is all the way at the end of our row. Neon is the 11th element. It's got 11 protons in its nucleus. If we look at neon's valence electrons, this is not neon. This is sodium. Sorry. Sodium is the 11th element. So sodium's got 11 protons in its valence shell. 11 protons in its nucleus. Sodium has 11 protons in its nucleus. If we look at its valence electrons, sodium has 1 valence electron. So he's got 1 electron in that valence shell, and he's got 10 core electrons. So we're looking at the interaction between these 11 protons in the nucleus and this 1 electron in the valence shell. And we can think of this interaction as a kind of a magnetic interaction. So this is positively charged, this is negatively charged, and these two are pulling into each other. They're attracted to each other. So for sodium here, the attraction is between a plus 11 in the nucleus and a -1 out here in the valence. So 11 attracted to 1 valence electron. Okay. If we were to do the same kind of scenario for neon, so neon now is going to be all the way at the right-hand side. So if we look at neon, nope, let's look at argon, excuse me. If we look at argon is going to have 18 protons in his nucleus. And then if we look at that valence shell out here, so we'll again have 10 electrons here. And then if we look at the valence shell out here, he's going to have 8 electrons out here in this valence shell. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, if we talk about the interaction, the magnetic interaction between 18 protons and 8 valence electrons, that's going to be a much stronger interaction than our 11 and 1 over here for sodium. So 11 and 1, a little bit attracted to each other. 18 and 8, extremely attracted to one another. So when we look at the trends going from left to right, here's our sodium. We would see there's a little bit of pull from those valence electrons into the nucleus. So the protons reach out, grab that valence electron, and try to attract it or pull it to the center. But if we go over here to argon, we've got a incredibly large pull into the center of this nucleus. So that nucleus is reaching out, it's pulling on those 8 valence electrons with its 18 protons, and it's hugging it in closer. So as we go from left to right on the periodic table, you can think of there being kind of a magnet or an arm reaching out to those valence electrons and pulling them closer, 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 closer. Then we add an energy level and we pull them in closer, 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 closer. And then we add an energy level. So left to right, we're reaching out, we're touching those valence electrons, and we're pulling on them with a greater force, causing that atomic radius to be smaller. That's, I think, where I'm going to leave it for atomic radius. We'll talk about metallic characteristic and ionization energy in future slides. I hope you guys found this helpful.